Today we're going to talk about the next part of graphing rationals. I'm going to talk, and if you want to listen, you're going to listen. We'll see. We're going to talk about horizontal asymptotes. Horizontal asymptotes are a little bit harder to find than the vertical asymptotes were, but totally doable. So, first things first. To find a horizontal asymptote, we compare the degree of the numerator to the degree of the denominator. In case you've forgotten, degree is the power of the highest exponent when you write your equation in standard form. So it needs to be all multiplied out, x squared minus 2x plus 5 kind of form. And then whatever's in front of that first variable is going to be the leading coefficient, and the power on it is going to be the degree. So once you have it in standard form, there's three possibilities that can occur. Okay, we're going to look at those three. The first one is what I'm going to refer to as option 1. It's when the degree of our numerator is less than the degree of our denominator, like x over x squared. The degree of the numerator there is 1 because it's like x to the first. The degree of the denominator is 2 because it's x squared. And since 1 is less than 2, the numerator is considered to be less than the degree of the denominator. What that tells us is anytime that is true, we have one horizontal asymptote always at the line y equals 0. Okay, one horizontal asymptote always at the line y equals 0 if the degree of the numerator is less than the degree of the denominator. The next possibility that can occur, or option 2, is that the degree of the numerator is equal to the degree of the denominator. So for example, if we have 4x squared over 2x squared, those are both second degrees. They are the exact same. And so what that tells us is there's one horizontal asymptote. In this case, when the degree is the same, we just take the leading coefficient of the numerator over the leading coefficient of the denominator. So I would do 4 divided by 2, and I would have a horizontal asymptote at y equals 2. Okay, y equals 2. The last one, option, is when our numerator degree is higher than the degree of the denominator. Okay, we're going to call that option 3. So an example of that would be 2x squared over 4x. Because the x squared has a power of 2, the x just has a power of 1. 2 is bigger than 1. In these cases, there's no horizontal asymptote. Doesn't exist. Instead, they have what we call a slant asymptote. We're not going to worry about equations for slant asymptotes. We're just going to say no horizontal asymptote has a slant asymptote. Now, to actually practice finding these, we're going to find all the horizontal asymptotes for the following function. So the first function we're given is this one. Okay, we're going to compare, like I said, the degree of the numerator to the degree of the denominator. In this case, the numerator doesn't really have a degree, 0, there's no x. The denominator has a degree of 2. So our numerator is less than our denominator, which means we're looking at option 1, which means we have one horizontal asymptote at y equals 0. Okay, so we just click one horizontal asymptote, y equals 0. Okay. Next example, if we have f of x equals the quantity 2x squared minus 5 over x plus 1 and x minus 1. Okay, now we want to compare these in standard form. It's not x squared over x. If I multiply it out, it's actually 2x squared minus 5 over x squared minus 1, which means that the degree of the numerator and the degree of the denominator is the exact same, which means what we do is we divide the leading coefficients to find the equation of the horizontal asymptote. So x squared has a coefficient of 1. 2x squared has a leading coefficient of 2. 2 divided by 1 gives me one horizontal asymptote at y equals 2. Okay, next example. If we have this equation, okay, when I look at this, I say, oh gosh, it's already in standard form, so I can just compare the degree of the numerator to the degree of the denominator. I have squared over 1, so the degree of the numerator is higher. That tells us there's no horizontal asymptote. I would click no horizontal asymptote. On Delta Math, I would be done. But we should know that instead, it has a slant asymptote. Okay? I actually think that's the hardest part of your assignment for today. But we're going to talk about finding x and y-intercepts also. So if I want to find x-intercepts for the rational function, I'm going to first simplify the fraction. I'm going to remove all wholes. And then I just set the numerator equal to 0 every time and solve. So, example, finding the x-intercepts. I have this equation. Like I said, I want to factor it first and remove all wholes. So I factor x squared minus 2x minus 3. I say, oh, it's x minus 3 times the quantity x plus 1 over this. Nothing cancels, okay? There's no wholes in this function. So I go ahead and I just set my numerator equal to 0. So I have x minus 3 equals 0. and x plus 1 equals 0. When I solve those, I get 2 x-intercepts. They're at 3, 0 and negative 1, 0. Straightforward enough, right? Okay, another example of finding the x-intercepts. If this is my equation, we said we always want to factor first to see if we can take out any holes. So when I factor this one, I pull out the GCF on the top, and I say, oh, 4x plus 8 becomes 4 times the quantity x plus 2, and then I factor the bottom. Now, this one does have a hole, if you remember our last lesson, because x plus 2 and x plus 2 can cancel, okay? So now, I could say, oh, there's a hole at x equals negative 2, so now I'm going to set the simplified numerator equal to 0. All that's left in my new numerator is the number 4. Since 4 is not equal to 0, the graph has no x-intercepts, okay? All right, last example on the x-intercepts. If this is my equation, can't factor it, it's already simplified, there's no holes, so I set my numerator equal to 0 and I solve. And I find out there's one x-intercept at 2/5, 0. Okay, so that's how we're going to do x-intercepts. Now, we're going to talk about finding y-intercepts, okay? Y-intercepts are done just like we've done for every single other function in our math universe. We plug a 0 in for x, and we evaluate. Looking at some examples of that. Ta-da! Okay, here's my equation. I'm going to plug 0 in for x and evaluate. Put 0 there, simplify, I get 4 over 2, which is 2. So I know there's one x-intercept at 0, 2. Last example for the day. We're finding the x-intercept again. Once again, just like we've always done it. Put 0 in for x and evaluate. So I get 0 plus 2. Make sure you follow order of operations. So I do the first set of parentheses, I do the second set of parentheses, then I multiply and simplify, and I get one x-intercept at 0, 1/3. Excellent. Woohoo!